Hi guys and girls, in this video I will tell you about physics as a science. Physics is a natural science that studies matter, its fundamental constitutes as its motion and behavior through space and time and the related entities of energy and force. Physics is one of the most fundamental scientific disciplines, with its main goal being to understand how the universe behaves. Physics is one of the oldest academic disciplines and taught its inclusion of astronomy, perhaps the oldest. Over much of the past millennia, physics, chemistry, biology, and certain branches of mathematics were a part of natural philosophy, but during the scientific revolution in the 17th century, those natural sciences emerged as unequal research and endeavors in their own right. Physics intersects with many interdisciplinary areas of research such as biophysics and quantum chemistry, and the boundaries of physics are not rigidly defined. New ideas in physics often explain the fundamental mechanism studied by other sciences and suggest new avenues of research in those and other academic disciplines, such as mathematics and philosophy. Advances in physics often enable advances in new technologies. For example, advances in the understanding of electromagnetism, solid state physics, and nuclear physics led directly to the development of new products that have dramatically transformed modern day society, such as television, computers, domestic applications, and nuclear weapons. Advances in thermodynamics led to the development of industrialization, and advances in mechanics inspired the development of calculus. History. The word physics comes from ancient Greek meaning knowledge of nature. Classical physics became a separate science when early modern Europeans used experimental and quantitative methods to discover what are now considered to be the lives of physics. Major developments in this period include the replacement of the geocentric model of the solar system with the heliocentric Copernican model, the laws governing the motion of planetary bodies, Galileo's pioneering work on telescopes and observational astronomy in the 16th and 17th centuries, and now Newton's discovery and unification of the laws of motion and universal gravitation. Newton also developed calculus, the mathematical study of change, which provided new mathematical methods for solving physical problems. The discovery of new laws in thermodynamics, chemistry, and electromagnetics resulted from greater research efforts during the Industrial Revolution as energy needs increased. The laws comprising classical physics remain very widely used for objects on everyday scales traveling at non-relativistic speeds. Since they provide a very close approximation in such situations, and theories such as quantum mechanics and the theory of relativity simply simplify to their classical equivalents at such scales. However, inaccuracies in classical mechanics for very small objects and very high velocities led to the development of modern physics in the 20th century. Modern physics began in the early 20th century with the work of Max Planck in quantum theory and Albert Einstein's theory of relativity. Both of those theories came about due to inaccuracy in classical mechanics in certain situations. Classical mechanics predicted a varying speed of light, which could not be resolved with the constant speed predicted by Maxwell's equations of electromagnetism. This discrepancy was corrected by Einstein's theory of special relativity, which replaced classical mechanics for fast-moving bodies and allowed for a constant speed of light. Black-body radiation provided another problem for classical physics, which was corrected when Planck proposed that the excitation of material oscillators is possible only in discrete steps proportional to their frequency. This, along with the photoelectric effect and a complete theory predicting discrete energy levels of electron orbitals, led to the theory of quantum mechanics taking over from classical physics at very small scales. Quantum mechanics would come to be pioneered by Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. From this early work and work in related fields, the standard model of particle physics was derived. Following the discovery of a particle with properties consistent with the Higgs boson at CERN in 2012, all fundamental particles predicted by the Standard Model and no others appear to exist. However, physics beyond the Standard Model with theories such as supersymmetry is an active area of research. Areas of mathematics in general are important to this field, such as the study of probabilities and groups. Core theories. Throughout physics deals with a wide variety of system contained theories are used by all physicists. Each of these theories was experimentally tested numerous times and found to be an adequate approximation of nature. For instance, the theory of classical mechanics accurately describes the motion of objects provided they are much larger than atoms and moving at much less than the speed of light. Those theories continue to be areas of active research today. Chaos theory, a remarkable aspect of classical mechanics, was discovered in the 20th century, 3 centuries after the original formulation of classical mechanics by Newton. Those central theories are important tools for research into more specialized topics, and any physicist, regardless of their specialization, is expected to be literate in them. Those include classical mechanics, quantum mechanics, thermodynamics and statistical mechanics, electromagnetism, and special relativity. Classical physics includes the traditional branches and topics that were recognized and well developed before the beginning of the 20th century. Classical mechanics, acoustics, optics, thermodynamics, and electromagnetism. Classical mechanics is concerned with bodies acted on by forces and bodies in motion and may be divided into statics, kinematics, and dynamics. The latter includes such branches as hydrostatistics, hydrodynamics, aerodynamics, and pneumatics. Acoustics is the study of how sound is produced, controlled, transmitted, and recovered. Important modern branches of acoustics include ultrasonics, the study of sound waves of very high frequencies beyond the range of human hearing, bioacoustics, the physics of animal calls and hearing, and electroacoustics, the manipulation of audible sound waves using electronics. Options: the study of light is concerned not only with visible light but also with infrared and ultraviolet radiation, which exhibit all of the phenomena of visible light except visibility, e.g., reflection, refraction, interference, diffraction, dispersion, and polarization of light. Heat is a form of energy, the internal energy possessed by the particles of which a substance is composed. Thermodynamics deals with the relationship between heat and other forms of energy. Electricity and magnetism have been studied as a single branch of physics since the intimate connection between them was discovered in the early 19th century. An electric current gives rise to a magnetic field, and changing magnetic field induces an electric current. Electrostatistics deals with electric charge at rest, electrodynamics with moving charges, and magnetostatistics with magnetic poles at rest. Modern physics. Classical physics is generally concerned with matter and energy on the normal scale of observation, while much of modern physics is concerned with the behavior of matter and energy under extreme conditions or on a very large or very small scale. For example, atomic and nuclear physics study matter on the smallest scale at which chemical elements can be identified. The physics of elementary particles is on an even smaller scale, since it is concerned with the most basic units of matter. This branch of physics is also known as high energy physics because of the extremely high energies necessary to produce many types of particles in particle accelerators. On this scale, ordinary commonsensical notions of space, time, matter, and energy are no longer valid. The two chief theories of modern physics present a different picture of the concepts of space, time, and matter from that presented by classical physics. Classical mechanics approximates nature as continuous, while quantum theory is concerned with the discrete nature of many phenomena at the atomic and subatomic level, and with the complementary aspect of particles and waves in the description of such phenomena. The theory of relativity is concerned with the description of phenomena that take place in a frame of reference that is in motion with respect to an observer. The special theory of relativity is concerned with motion in the absence of gravitational fields, and the general theory of relativity with motion and connection with gravitation. Both quantum theory and the theory of relativity find applications in all areas of modern physics. While physics aims to discover universal laws, its theories lie in explicit domains of applicability. Loosely speaking, the laws of classical physics accurately describe systems whose important lengths scales are greater than the atomic scale, and whose motions are much slower than the speed of light. Outside of this domain, observations do not match predictions provided by classical mechanics. Einstein contributed the framework of special relativity, which replaced notions of absolute time and space with space-time, and allowed an accurate description of systems whose components have speeds approaching the speed of light. Planck, Schrödinger, and others introduced quantum mechanics, a probabilistic notion of particles and interactions that allowed an accurate description of atomic and subatomic scales. Later, quantum field theory unified quantum mechanics and special relativity. General relativity allowed for a dynamical curved spacetime with which highly massive systems and the large-scale structure of the universe can be well described. General relativity has not yet been unfiled. With the other fundamental descriptions, several candidate theories of quantum gravity are being developed. Relation to the other fields. Prerequisite. Mathematics provides a compact and exact language used to describe the order in nature. This was noted and advocated by Pythagoras, Plato, Galileo, and Newton. Physics uses mathematics to organize and formulate experimental results. From those results, precise or estimated solutions are obtained or quantitative results from which new predictions can be made and experimentally confirmed or negated. The results from physics experiments are numerical data with their units of measure and estimates of the errors in the measurements. Technologies based on mathematics like computation have made computational physics an active area of research. Ontology is prerequisite for physics, but not for mathematics. It means physics is ultimately concerned with descriptions of the real world, while mathematics is concerned with abstract patterns, even beyond the real world. Truth physics statements are synthetic, while mathematical statements are analytical. Mathematics contains hypotheses, while physics contains theories. Mathematics statements have to be only logically true, while predictions of physics statements must match observed and experimental data. That is all. Thank you for watching. Goodbye.